I'm Leonardo and I'm from the University of Trento. So are you able to see my screen?
Yes.
Okay, perfect. So as Ricardo said, what I will talk about today is this talk about identification and characterization of a lunar cave by using synthetic aperture radar imaging. So as some of you may know, we published this article quite recently, and so we'll talk about it, where we basically we found evidence through the radar of conduit on the moon below the Mare Tranquillitatis pit. I would like to mention that this is a collaborative effort among an interdisciplinary group, and so I would like to thank the co-authors, which are Riccardo Pozzobon, Francesco Sauro, Davide Castelletti, Gerald Wesley-Patterson, and Lorenzo Briccone. So, of course, I would like to give an outline of the talk. So I will give an introduction on the motivation about this work. Then I will explain the methodology and how we detected a cave on the moon. And then I will discuss the validation that we undergone with the terrestrial analogs, and then how we estimated the cave parameters and how we did the three-dimensional reconstruction. And then I will talk briefly about conclusions and next steps of this work. So what is the motivation? Well, many pits have been identified on the surface of the moon, as you can see here. And these pits were identified mainly by optical images. But from optical images, unfortunately, it's difficult, if not impossible, to understand whether there is a cave conduit below this pit. So whether there is an extensive subsurface volume. So how we can address this problem with a different type of sensor? Well, what we did, so we started from this question. So first question is that, is there any cave conduits with extensive underground volume at the base of the pits? And then the second question is that, if there is a conduit there, is that conduit accessible? So the main idea was to use a different kind of sensor from optical to make a survey. And so we use synthetic aperture radar. What is nice for this application for a synthetic aperture radar is that we can exploit the side-looking geometry. So the radar looks tilted on the surface. And so maybe we can identify any possible signature from this tilted acquisition geometry. And then from the image, the idea was like to study the reflections coming from the pit, the radar reflection, to understand whether we can infer some geological information and reveal the structure and geomorphology of the bottom of the pit. This is a scheme highlighting the general idea. So we have this orbital sensor. So we have a radar-mounted spaceborne platform, and then it's looking, it's side-looking over the surface of the moon. So given the tilted acquisition geometry, we could actually see reflections, radar reflection coming from the putative conduit, from the putative cave. And we investigated the Mare Tranquillitatis pit, which I showed here. So we were investigating this pit. So as I said, we use a synthetic aperture radar, and we use the sensor is called Mini-RF. Mini-RF, it's a sensor operating in the microwave frequency range around 2 gigahertz. And also, is able to exploit polarimetry, and the image resolution, which is quite important parameter, is 50 by 30 meters. And the look angle, so the acquisition geometry, the angle at which he was looking at the surface is 47.6 degrees. So how we identified the cave on the Mini-RF image? Well, first we have a SAR image of the surface, and then what we do is that we look for anomalies in the image. And then we perform 3D radar simulations, because we know the acquisition geometry, by exploiting a digital terrain model of the surface, of the lunar surface, obtained by other sensors. Then what we do is that we compare the Mini-RF image, so the experimental data, with our simulated images to understand whether there is a matching, and we basically can detect the cave and its morphological parameters. So as I said, we focused on the Mare Tranquillitatis pit, which is actually quite close to the Apollo 11 landing site. and of course it's in the Mare Tranquillitatis region of the moon. So how we started this research? Well, we knew from optical image there was a pit, of course, and then here on the right you can see the mini-RF SAR image. As you can see here, it's quite a blurry image, but you can see here the center of the pit, and then on the left we have this quite strange and bright anomaly from the peak. This bright anomaly means that there was a lot of power coming from this side of the pit back to the radar. So given this, how we can tell that there is a cave conduit? As I said, this is the mini-RF image. And then we add as auxiliary information the digital terrain model derived from the optical camera. And what we did is that we form a simulation of the radar acquisition by exploiting the DTM. And this, on the right, should be the image acquired by mini-RF based on the fact that from the DTM. So if we add only the surface, this would be the mini-RF image. But as you can see here, we have more information. So now the question is where this information comes from. So what we did, as I said, we did many simulations, and then we ended up with two possible models for the cave. One we call Model A and one we call Model B. The difference between two models are the conduit parameters here that we characterized. So in a way, how we validated our technique? So how do we knew that in fact these anomalies on the left were coming from the cave? Well, what we did before is that we spent many years analyzing similar images acquired on Earth by a similar synthetic aperture radar sensor. So we had two similar sensors, one orbiting Earth and one orbiting the moon. And so we acquired images over some collapsed lava tube sections here. Here I show an example of Lanzarote. And then you can see here on the right, the radar image corresponding to the optical image. And you can see also on Earth, like if you see here, the points are marked with the stars, you can see here that you have some anomalies in the image, as you have seen on the moon image. So for instance, if you focus on this part here, you can see here you have this anomaly. And if I go back here, you can see you have quite similar anomaly. So in a way, we had a really extensive validation on Earth on how to interpret these images anomaly over radar data. And here you can see another study we did on Earth, also on Lanzarote. So on top, you can see the radar image. And on the bottom plot, you can see the superimposition of the radar image with the LiDAR data. And you can see that these bright anomalies in the radar image actually correspond to the LiDAR parts of the subsurface. And here you can see another validation where on top, you can see the simulated radar image of the surface without the subsurface model from the LiDAR. And here you can see both surface and subsurface model from the LiDAR simulated. And you can see here that by doing this experiment, you can see here that these parts are actually originating from the subsurface, LiDAR subsurface model. So given this, we arrived at some conclusion that from the radar image, as we were observing on Earth, also on the moon, we were actually looking with the radar inside the cave. And so the next step was like, okay, we identified that there could be a cave there, but how we can estimate the cave parameters? And as I said, we conducted a series of radar simulations for understanding the cave parameters, but we didn't start from scratch. As I said, we had the digital terrain model of the surface, but also another very important information, which is this overhang model computed by Wagner and Robinson by using stereo cameras. So we had a partial model of the pit. Well, we had a full model of the surface and a partial model of the overhang of the pit. Actually, the mini-RF image we had could only look on the left side of the pit. So we could only explore the left part here. So how we could estimate the cave parameters from the image? Well, first, as I said, we had a radar theoretical framework for determining the cave parameters. And so we could invert to understand these yellow parts here that we model. But unfortunately, we had a problem because SAR images measure a 3D space, but it's projected actually over a 2D plane. So it's inherently ambiguous. And so we had to explore a parametric space for actually understanding the slope of this cave roof and floor model. And here you can see a geometric scheme aligning the surface, the model we had, and the part of the conduit we would like to determine. So how we did that? Well, we parameterized the cave parameters. So we had a parameterization for these two parts of the conduit. And then we generated a 3D model of the Mare Tranquillitatis pit, which of course included the model from Wagner and Robinson. And then what we did, we performed a 3D radar simulation by also, of course, considering the mini-ref parameters. And so we got a simulated radar image of the pit. And then from this simulated image, mini-ref image, we performed correlation analysis against the actual experimental radar image to find the best model. So we had a number of simulated models with different shapes of the conduit, and we compared the radar simulation based on this model with the actual radar image to find the best model. And here you can see actually some examples of the models we explored. On the left, you can see the actual mini-ref image acquired over the Mare Tranquillitatis pit. And here you can see the simulation that we performed by considering a model which only contained the surface and the overhang of the pit. You can see that here there is a missing part, okay? So part of the response here is missing from the simulation. What it means that there is something more here that is reflecting a power towards the radar. You have reflections from here. And here you can see a simulation with a model that had a roof, here we call this the roof, and slope floor of about 80 degrees. But this model, this is an example of a model that was not matching because once again, there is part of the response that is missing when we compare it to the mini-ref image. And this is another model with a roof and a floor slope of about 50 degrees, and you can see sort of matches, but still not there to match the red pattern, which is the anomaly shape, this anomaly shape. So what we did, we generated a number of models, and without entering in the details of this plot, the main message is that you can see here, for instance, on the right, the roof slope, and here you can see the correlation value. We had two best models. Why we had two best models? Because the measurement of the radar are inherently ambiguous. They can only measure distances on the 2D space. Okay, but nevertheless, we had very good correlation for two models. So given the two models, apart from the conduit roof and slope, roof and floor slope, we could also determine the conduit width. Now, what is really fascinating, in my opinion, is that we estimated that the conduit width should be at least 50 meters. But given the geometry of the acquisition, actually, we believe that the conduit width is actually underestimated from the radar measurements. And so there are models with larger conduit width that still can explain the observation. So we found out that the cave conduit width is at least 50 meters, but we cannot say whether it's 100, 200, or even more. So to summarize this part, through matching between simulation and real data, we were able to find two best models that fit the observation. One, which we call Model A, has a floor slope here of about 3 degrees. The maximum depth of the conduit is about 135 meters, and the conduit extends for at least 25 meters. So why we say at least 25 meters? Because the radar waves propagate into the conduit, but due to the geometry, at some point, the signal does not get reflected back. But this does not mean that maybe the cave conduit extends further. It's just an effect of the geometry. And then we had the second model, best model, which called Model B, which is much more inclined than the Model A. And so it has a roof and floor slope of about 50 degrees, and maximum depth is about 175 meters, with a conduit extension of at least 77 meters. So from the radar data, from pure geometric observation, we have these two models. But in terms of geology, what could be the most likely model apart from the radar-derived geometry? So what we believe is that the model B scenario, this one, it's more likely. Why it's more likely? Because if you have this collapse pit, then it means that you should have some collapse material, okay? And so this collapse material should have gone somewhere into the surface. And so the volume occupied should be at least the one that it was before collapsing. So the detrital cone material is more compatible with the second case, with this case. And so in a way, it's the model B is more compatible with the natural characteristics of a pit that formed due to the collapse of a conduit ceiling. And it's also more in line, this is quite interesting, with the camera observation on the other side of the pit. Now, from stereo camera, they were able to map the overhang of the pit, but not quite likely the inside. But the authors of that study, well, they were basically saying that maybe there is a secondary overhang here, you can see in orange. We are not sure about it, but there could be. And our observation on the other side quite match their theory, not confirmed, that there should be a sloping overhang on the other side. So now the question could be why we detected a cave conduit only over the Mare Tranquillitatis pit. What about the other pits? So the issue we had with the mini-RF data is that mini-RF is a sensor that was not designed to explore lunar pits. It was actually designed to find water at the lunar poles. And so it has a resolution that is not good enough to explore all the lunar pits. And also the data is really scarce around equatorial region. So what I put here is a list, a partial list of all the lunar pits. And in orange, you can see the ones not resolvable by mini-RF, and in blue, the one that has no coverage. So the only pits that we could explore with mini-RF were a bunch, were about 5 or 6. And in fact, over these pits, we could not have a conduit evidence, but that was expected from previous studies based on the degradation state that were telling that probably that part of the pit, it's blocked. So there was material blocking the entrance. And so this was compatible with our observation. So what's next? So we use this spaceborne sensor called synthetic aperture radar that is able to produce images of a given surface to find lunar pits. Unfortunately, we used a sensor that with a really scarce resolution of about 50 by 30 meters. So what is the next step? Well, we know from Earth observation, for Earth observation, we use very similar radar technology, but with a resolution of about alpha meter of alpha meter. And here you can see another study we did over the well of Barut in Yemen, which is, you can see here the inside, where we were able with the SAR to map the overhang and the floor of the pit by using spaceborne observation. So we can actually deploy a similar technology in moon orbit. So in a way, we invented a new technique to find caves, which is like using side-looking SAR. But for looking underground, there is another technique, which is called orbital ground penetrating radar. So these two can very well complement together because the side-looking SAR can actually map the cave characteristics and accessibility information in the proximity of pits, while the orbital ground penetrating radar is able to potentially map the conduit caves far from the pits because it's able to propagate through ground. Because SAR, this side-looking SAR is not able to, the waves are at a frequency such it's not able to propagate through ground. And here I show some examples of simulated subsurface conduit, how they should look like in an orbital ground penetrating radar observation. And also, like, we know that these sensors are quite reliable in detecting subsurface voids. So the combination of these two class radar sensors could be very good, really excellent for mapping additional lunar caves. And just to mention, there is this quite interesting project called LUGO, LUGO is a mission initiative from ESA, which has on board one of these orbital GPR that I was mentioning. And the resolution is quite interesting because it's a factor of 10 better of what we have now on the moon, which is the Lunar Radar Sounder operated by JAXA. So this is just to tell there are several initiatives for locating tubes on the moon. And so one sensor could be this one, and maybe we can get another side-looking SAR with better resolution to have a perfect combination for finding more subsurface conduit on the moon. So to conclude this seminar, after more than 50 years, because more than 50 years ago, it was theorized that there were like these sort of lunar tubes, lunar conduits, we were able to prove the existence of one of them below the Mare Tranquillitatis pit by using side-looking synthetic aperture radar imaging. And how we did that? Well, we actually invented a cave detection technique based on SAR imaging, which we validated by using terrestrial data. And we knew that we proved that this methodology was able to reliably estimate the cave parameters close to skylights. So we applied this technique on mini-RF data acquired on the moon, and we found a cave conduit below the MTP. And we found that the best model has a roof slope of about 55 degrees and a floor slope of about 45 degrees. And the conduit extends at the very least 77 meters in the lunar surface. It could be more, but we don't know because we have this phenomenal radar signal extinction. Mini-RF, as I said, was not designed for surveying lunar pit. We actually took this data from 15 years ago, and we looked again at it, and we found the cave. And why it's not designed? Well, it has 50 battalion meter resolution, so it's really not good for studying lunar pit. And also the coverage was really scarce. So this work here represents actually a starting point for identifying lunar caves, and we need more sensors orbiting around the moon to characterize if there are other conduits, as I said. So to conclude, this is also a really promising technique for other planetary bodies because basically it's a technique, as I said, that allows to characterize caves in the proximity of skylights. But what is fascinating is that also on Mars, there are skylights, and so there could be cave conduits. So maybe in the future, we can use the very same SAR imaging technique to characterize also Martian caves if they are there from space. So this concludes my talk today, and thank you for your attention.